Welcome to Lecture 16, Section 3.3 of the Text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert Eyabi. Section 3.3 Subgroups Definition. Let G be a group with respect to the binary operation star. We say that the subset of G, H, is a subgroup of G if H forms a group with respect to the same binary operation star. There are a couple of things in this definition that I want to point out very quickly. Number one, if H is a subgroup of G, then we know that, of course, H is a subset of G. And number two, all the axioms of a group hold in H with respect to the same binary operation star. And thirdly, because H is a group, H has an identity element. But there is something unique about that identity element. Recall that we proved in 3.2 that the identity element of a group is unique. So G is a group. It has an identity element. H is a subset of G. H is also a group in its own right. It has an identity element. Are these identity elements the same? Yes, they are. As a matter of fact, if there are n different subgroups of G, they all have identity elements, and the identity element is going to be the exact same identity element of G. Interesting. Examples. Let G be an arbitrary group. Then the following subsets of G, H, the singleton, with its only element being the identity element, and H being the group itself, are called the trivial subgroups of G. So we can conclude that every group has at least two subgroups. And the two subgroups are the trivial subgroups. The subgroup made up of the identity element and the subgroup which is the group itself. What about non-trivial subgroups? Example 2. If G is the set of integers under the binary operation addition, then we can quickly verify that Z under plus is a group. Now, I want you to verify that the subset of Z, known as the set of even numbers, is a subgroup of Z, the set of integers. What are you supposed to verify? Number one, it is clear that the set of even numbers is a subset of Z. You now go ahead and verify closure. Associativity is hereditary. It has identity element, and every element has an inverse under the binary operation addition. Now, since we already know that G is a group, to verify that H is a subgroup of G, do we have to go through all four axioms that define a group? For example, associativity is hereditary. If G is associative and H is a subset of G, then H is obviously associative. Can we even reduce that some more? Subsection 3.3.2 Theorem, which is also known as the subgroup criterion, i.e., if you want to prove that a subset of a group is a subgroup, all you have to do is verify that these three properties hold for that subset H. What are the three properties? Number one, H is non-empty. Number two, for every xy in H, xy is in H, that's closure. And number three, for every x in H, x inverse is in H, the existence of inverses in H. So, if we can prove this theorem, that means from now on, you do not have to verify all four axioms to determine that H is a subgroup of a group G. All you have to do is, number one, show that H is non-empty. Number two, show that H is closed. And number three, show that H has inverses. And we shall even compress this further. But let's go ahead and prove this beautiful theorem. Forward direction. Suppose H is a subgroup of the group G. We must show that conditions 1, 2, and 3 hold in H. Okay, so let's start with condition 1. If H is a subgroup, then H is a group in its own right. And as a group, it has the identity element. Therefore, it is non-empty. Condition 1 holds. That was easy. Condition 2, we prove closure. Well, if H is a subgroup, then it is a group in its own right. And as a group, the second axiom that defines a group is closure. So for every xy in H, since H is a group in its own right, xy is in H. Therefore, closure holds in H. 3, we have to prove the existence of inverses. Let X be in H. Again, H is a group, and the fourth axiom that defines a group is that groups contain inverses. So if H is a group and X is an element in H, then obviously X inverse is in H. So conditions 1, 2, 3 hold, and the forward direction is done. The reverse direction is going to be more interesting. Suppose conditions 1, 2, and 3 hold. Can we prove that H is a subgroup of G? Reverse direction. Suppose H is a subset of G and conditions 1, 2, and 3 hold in H. To show that H is a subgroup of G, we need only show that H is a group. It is already a subset, so all we have to do is prove that H is a group. Verify the 4 axioms that together define a group. Axiom number 1, closure. We have to prove that H is closed. But by condition 3, if X is in H and Y is in H, XY is in H. That is the definition of closure. So closure is done. 1 down, 3 to go. Axiom 2, we have to prove that star is associative. Well, G is associative as a group. H is a subset of G, so H is associative. Done. 2 down, 2 to go. Axiom 3, existence of the identity element E. By condition 1, again, this is condition 1, H is non-empty. That means there exists an element A in H. So, by condition 1, H is non-empty, so there exists an element A in H. But again, by condition 3, if X is in H, then X inverse exists and X inverse is also in H. So by condition 1, since H is non-empty, there exists an element A in H. And by condition 3, the inverse of that element exists and it is also in H. But A in H, A inverse in H by condition 2. If X is in H, Y is in H, XY is in H. So, if A is in H, A inverse is in H, by condition 2, A times A inverse is an element in H. But what is A times A inverse? E. So, we have E in H. Axiom 4, existence of inverses. Well, that is clearly condition 3. Condition 3 says if X is in H, then X inverse exists and it is also in H. And that is the last axiom for a group, and that proves the theorem. That is the subgroup criterion. So from now on, if we want to prove that a subset H of a group G is a subgroup, all we have to do is show that H is non-empty, show closure and existence of inverses. And we shall even do better. Subsection 3.3.3 Theorem. Subgroup criterion compressed. A subset H of G is called a subgroup of G if and only if, number one, H is non-empty. Number two, if A is an element in H, B is an element in H, A times B inverse is an element in H. Wow. So I do not even have to verify three conditions. Two would be enough. Observe that condition 2 here is actually compressing conditions 2 and 3 in the previous theorem. We are dealing with closure and existence of inverses at the same time. So from now on, I would mostly use Theorem 3.3.3 to prove that H is a subgroup of a group G. Proof. The proof is similar to the one for Theorem 3.3.2, and I'm going to leave this as a simple reading exercise for serious students. You can go to page 162 of your text, Elements of Modern Algebra by Gilbert and Gilbert, 8th edition, to see the proof, but you should be able to do it on your own. It's actually exciting, but I'm not going to do it here. Let's take a little example. Let the set of all H lambda, lambda is from the indexing set L, be an arbitrary non-empty collection of subgroups H lambda of the group G, and define K to be the intersection of all these subgroups over lambda. Prove that K is a subgroup of G. So all the H lambdas are subgroups. So all I want you to prove here is that the intersection of subgroups is a subgroup. Very easy proof. Let's do it. We are going to use Theorem 3.3.3 to prove that the intersection of subgroups is a subgroup. We shall show that K is non-empty, and we shall show that if we pick any two elements A and B in K, AB inverse would be an element in K. Condition 1, we have to prove that K is non-empty. Since the H lambdas are subgroups of G, that means E is an element in H lambda for every lambda in the indexing set L. Remember, I told you this at the very beginning of this lecture. Since G is a group, G has an identity element E. Each of the subgroups H lambda of G would also have this same identity element E. So E is an element in H lambda for every lambda in L. In other words, the intersection of all the H lambdas would have at least one element, E. Again, the intersection of all the H lambdas is K. What does that mean? E is an element in K, and therefore K is non-empty. This proves condition 1. Condition 2. Suppose A and B are elements in K, required to prove A times B inverse is an element in K. But A and B, an element in K, and K being the intersection of all the H lambdas over lambda, that means AB is an element in the intersection of all the H lambdas. But by definition of the intersection, that simply means A and B are elements in H lambda for every lambda. But all the H lambdas are subgroups. Therefore, A times B inverse would be in H lambda for every lambda because they are all subgroups by the subgroup criterion compressed. But if AB inverse is in H lambda for every lambda, that simply means AB inverse is in the intersection of all the H lambdas. And that intersection of all the H lambdas is your K, i.e., AB inverse is an element in K. We have shown that K is not empty, And we have also shown that if we pick any two elements, A, B in K, AB inverse is in K, and therefore by the subgroup criterion compressed, K is a subgroup of our group G, and we are done. There are two special subgroups of an arbitrary group G that we would like to define. 3.3.4 definition: the center of a group. For any group G, the set of elements that commute with every element of G is called the center of G and denoted by ZG, i.e., ZG is the set of all elements A in G such that A commutes with every element in G. AX equals XA for every X in G. So you have to master the defining property of elements in ZG. When do we say an element belongs to ZG? An element belongs to ZG if that element star X equals X star that element. Then we say it belongs to ZG. That is the center of a group. 3.3.5 theorem. The center of a group ZG is an abelian subgroup of G. Proof. There are two things we have to prove here. Number one, that ZG is a subgroup of G, and number two, that it is abelian. By the definition of ZG, ZG is abelian. ZG is commutative. You can verify that for every AB in ZG, AB equals BA. And I'll leave that as a simple exercise for serious students. We would go ahead and verify that ZG is a subgroup of G. That is the one I'm really interested in. Once more, I'm going to use the subgroup criterion compressed. So the first condition we have to verify is that ZG is non-empty, i.e., we can find an element in ZG. Well, I claim that the identity element of my group G is actually in ZG. Why? Because E times X equals X times E for every X in G. So since E times X equals X times E, that means E must be an element in ZG. And that implies ZG is non-empty. Condition 1, verified. Condition 2, let A and B be elements in ZG. We must show that AB inverse is an element in ZG. Now, an element in ZG implies that AX equals XA for every X in G. That is how elements in ZG are defined. Call that equation 1. B, an element in ZG, implies that BX equals XB for every X in G. Call that equation 2. We want to show that AB inverse is an element in ZG. What does that actually mean? We want to show that AB inverse, all of that, X equals X times AB inverse. That is how elements in ZG are defined. And that happens for every X in G. So this is what we want to prove. We're going to start with the left-hand side and show that the left-hand side equals the right-hand side. But first, the technique we would use is to prove that B inverse is in ZG, i.e., we want to show that B inverse X equals XB inverse. Then we shall use that knowledge to prove that AB inverse X equals XAB inverse. Here is the procedure. From equation 2, Bx equals Xb. Now observe that ZG is a subset of G and G is a group. So A and B from ZG also means that A and B are from G, and because G is a group, both A and B have inverses. So their inverses exist. So multiply from the left by B inverse and from the right by B inverse. then we would have B inverse times BX, multiply that by B inverse, equals B inverse XB, B inverse. By associativity in the group G, since all these elements are also elements in G, we have B inverse BX times B inverse equals B inverse X times B inverse. But B inverse B is E, the identity, and B inverse is also E, the identity. And that simply implies XB inverse equals B inverse X. Or we can say B inverse X equals XB inverse. That satisfies the definition of elements in ZG. So we conclude that B inverse is an element in ZG. Now let's go ahead and prove that AB inverse X equals XAB inverse. AB inverse X equals A. By associativity in G, we put B inverse and X together. But B inverse is in ZG, so B inverse X is the same as XB inverse. Again, by associativity, we group A and X, leave B inverse all by itself. Since A is in ZG, AX is the same as XA. So we have XAB inverse. Again, by associativity in G, we group A and B inverse, and we have XAB inverse. We just proved that AB inverse, all of that in parentheses, times X equals X times AB inverse. Therefore, AB inverse is an element in ZG, and we conclude that ZG is a subgroup of G. Very interesting. Subsection 3.3.6 definition. This is the second special subgroup we would like to define. It is known as the centralizer of a group element. For a fixed element A of a group G, the set of all elements in G that commute with A is called the centralizer of A in G and is denoted by CA. So CA is the set of all elements in G such that A times X equals X times A. I want you to figure out the difference between ZG and CA. For CA, there is a fixed element A, and elements in CA commute with A. That was not the case with ZG. So the defining property for CA, X is in CA if and only if A times X equals X times A. X commutes with A. Subsection 3.3.7 Theorem. For a fixed element A, CA is a subgroup of G. The proof follows a very similar argument as the one we used for Theorem 3.3.5 above. So I'm going to leave that as a simple exercise for serious students. Problem. Let G be a group and let A be an element in G. Define the subset H of G by H equals the set of all elements X in G such that X is A to the N. N is some integer. In other words, H is the set of all elements of the form AN. Prove that H is a subgroup of G. Well, set X to be the element A raised to the power 1. Then X is clearly an element in H because we can write it as A to the 1 and 1 is an integer, so H is non-empty. Let's verify condition 2. Suppose X and Y are elements of H. We have to verify that XY inverse is an element in H. When would XY inverse be an element in H? If I can write XY inverse as A raised to the power N for some integer N. But X in H, Y in H implies that there exists some integers N1, N2 such that I can write X as A raised to the power N1 and I can write y as a raised to the power n2. Therefore, x times y inverse would be a raised to the n1 times a raised to the n2, all of these raised to the -1. By properties of exponents, that is a raised to the n1 times a raised to the -n2. Again, by properties of exponents, that will simply be a raised to the n1 minus n2. n1 is an integer, n2 is an integer. The difference of two integers is an integer, so we can call n1 minus n2 n-wiggle, and that would be an integer. So we have succeeded to write xy inverse as a raised to the power n-wiggle, where n-wiggle is your integer. Therefore, by the definition of elements in H, xy inverse is in H. It's not empty. For every xy in H, xy inverse is in H. Therefore, we conclude that H is a subgroup of G. As easy as that. And I would expect you to do this for many subsets of a given group G. A few observations about the subgroup H. As a matter of fact, it is also a special subgroup. Observe that if x is an element in H, then x is written as a to the n, where n is an integer. So we say that H is a set of all x in G such that x equals a to the n is in Z. In other words, H is a set of all elements of the form a to the n, where n is in Z. So if I break that down completely, the elements in H are of the form a0, a1, a2, and to my left, a to the -1, a to the -2, and so on and so forth, and it goes forever. So every element in H has something to do with a. It has to be in the form a raised to the power n, where n is an integer. See how important a is to the subgroup H. We call H a subgroup generated by A, and this is the notation of a subgroup that is generated by A. And that leads us to subsection 3.3.8 definition. Let G be a group. For every A in G, let us look at the subgroup H, which is defined as the set of all elements in G such that x equals a to the n, where n is an integer. Then, as we mentioned before, H is a subgroup generated by the element A and denoted as follows. We say that the element A is a generator of the subgroup H. We say that a subgroup K of G is a cyclic subgroup if there exists an element B in G such that K is generated by B. So G itself could actually be a cyclic group. And in that case, we say that G is a cyclic group if there is an element A in G such that G is generated by the element A, i.e., for every element X in G, X is written as A raised to the power N. Observation. If G is an additive group and H is a cyclic subgroup of G generated by A, then H is defined as the set of all elements in G such that X equals NA. For multiplicative groups, H is defined as the set of all X in G such that X equals A raised to the power N. For an additive group, H is defined as the set of all X in G such that X equals NA. And that subgroup is generated by A. Now, we have shown that if G is a multiplicative group and H is defined as follows, then H is a subgroup of G. Now, I want you to prove that if G is an additive group and H is defined as follows under the operation addition, H is a subgroup. Now, if H is defined as the set of all X in G such that X equals NA, then we are saying that if I pick any element X in G, I can always write the element as NA for some integer N. In other words, H is the set of all elements of the form NA, where N is an integer. And I can open that up, and that would be 0 times A, 1 times A, 2 times A, 3 times A, negative 1 times A, negative 2 times A, negative 3 times A, and so on and so forth. Example, observe that a set of integers is generated by 1 and also generated by negative 1 under addition. Why? If I pick any element X in Z, I can write X as NA. My A is 1, my N is X. I can write X as negative X times negative 1. My N is negative X, my A is negative 1. So A equals 1 generates Z, and also A equals negative 1 generates Z. This is just the introduction of cyclic groups. The entire section 3.4 is on cyclic groups. So we shall come back to this in 3.4. Thank you, and God bless you.